Oh my God.
All right, and we're back in our seats. So we're going to knock out these notes because I think you have about 9 questions to answer based on a graph, and I'll teach you exactly how to read that graph. All right, so we're going to skip the activity on page 22. Not because it's pointless, not because it's a really good activity, but just because I see where we're at, how much time we have. So I'm not going to assign page 22, but as far as like a test review, it's basically this thing right here. So you have a word bank, you have all the material world. You can classify it based on pure substances or mixtures, just like we did. Pure substances can be subdivided into elements and compounds. And mixtures, yesterday we said, could be heterogeneous or homogeneous. Today, we're going to take this a step further. You can kind of subdivide homogeneous, and you can kind of subdivide heterogeneous. So we'll take a couple slides of notes on that, and then we're going to start talking about homogeneous mixtures, which another name for that would be a solution. So the graphic organizer is on page 22 in your packet, not slide 22, but page 22. But we're going to skip that activity just because we're short on time. But if you wanted to do it and check it, this would basically, the first slide would be basically the answer key to that, okay? So we're going to pick up with slide 36. All right, we talked about mixtures, the 2 types of mixtures. Oh, subclassification of homogeneous mixtures. A solution is another name. A true homogeneous mixture could be called a solution. The key thing is, if you look at the atomic level, like all these little atoms and molecules hanging from the ceiling, a solution is made up of particles that are broken up that small. They're either the size of atoms or the size of molecules. They're super tiny. For that reason, they're not going to display the Tyndall effect. At this point, that probably means nothing to you, but in 2 slides, I'll show you a picture. When you shine light through a solution, light is pretty small, like a light wave, but molecules and atoms are even smaller. So they're so small that the light doesn't bounce into them. It goes straight through the solution, so therefore you can't see the light or the laser in the solution. Examples would be salt water, Kool-Aid. If you've ever made those at home, that is a true solution, which is a homogeneous mixture. Did I go too fast? Or are we good? Good? All right, the other type of homogeneous mixture is called a colloid. So we're adding like an extra branch under homogeneous mixture. What is a colloid? It looks homogeneous to the naked eye. But if you would like look at it under a microscope, it would look different. So under a microscope, it would appear heterogeneous. Why? Because the little particles are not the sizes of atoms and molecules. They're that like clumped together. So they're groups of atoms. They're groups of molecules, which are much bigger. So when you shine light through the sample, light is going to bounce into those little clumps, and it's going to bounce up, and then it hits another clump, it bounces down, hits another clump, bounces up and down. And because it's bouncing through the solution, you'll be able to see a beam of light in the solution. So the colloids have the Tyndall effect. True solutions would not. Good examples: Jell-O, mayonnaise, fog, butter, whipped cream. They're mixtures. And if you had to decide, are they solids, liquids, or gases, you might have a hard time with that. And the reason you would have a hard time with it is because they're kind of a mixture of 2 things. Like, would you agree you can cut Jell-O into like little squares, or you can make like a little race car, like a Jell-O jiggler? So it looks like a solid. You can cut it like a solid, but yet when you pick it up, it kind of jiggles and kind of acts like a liquid. Well, that's because it's really a mixture of 2 different things, part liquid, part solid. All right, here's an example of the Tyndall effect. You're going to want to label your picture as a colloid versus a solution. Now, how did I know it was a colloid on the left? Because I see the beam of light, which means there's little groups of particles. I can't see them with my naked eye, but if I looked at this, do you see how it's kind of cloudy? It's a little bit cloudy. If I looked at it under a microscope, I'd be able to see these microscopic particles. And when the light, the laser bounces into them, it goes up and down, up and down, up and down. And that's that light beam that you're seeing in the colloid. Whereas a solution, the particles are the sizes of atoms. And because that, the laser beam goes straight through, it doesn't bounce up or down, so you can't see it. Good example would be like in a movie with a bank robber. Let's say there's a laser set up, a security system surrounding the vault. You can't see the lasers. So what does a bank robber do? They like spray dust or chalk into the air, and those little clumps of particles bounce into the laser light, allowing them to see the laser beam. Anybody ever go to a light show like Downtown Lit? It's like one of the light shows. Before they do the light show, what do they often do? It would not look fun if they just went out on a crystal clear night and started shining lights up in the sky. Everyone would boo and go home. They put fog into the air, or they do fireworks that have a lot of smoke. So then when they shine the big lights up in the sky, it bounces off of those because that sky, that cloudy sky, that foggy sky would be considered a colloid. Clumps of particles. Questions on the difference? All right, here was a picture I took on the Appalachian Trail. Again, normally we don't see these beams of light. They're not caused by the sunlight hitting the leaves. It's because it was a pretty foggy morning. The sunlight bounces into those little clumps of moisture in the air, and that allows you to see those beams of light. Maybe that happens in your bedroom. You forget to clean, your room's kind of dusty, the sunlight goes in through the window, bounces off the dust particles, and you can see those streams or beams of light. Now, this is going to be beyond the scope of a test or a quiz. You're not going to have to identify what type of colloid it is, but I would just want to show this to you that not everything's black or white. You can't say, well, something's a solid, a liquid, or a gas when you're talking about mixtures. It can kind of be some gray area in between. So a good example would be fog. Okay, it's mainly a gas, right? That's the big dispersing medium. But what's in it would be a liquid, like little droplets of water, or little like mist in there. So that would be called an aerosol. Why? Because aero means gas. Sol is related to solutions. Smoke would be a solid aerosol, or like if you have athlete's foot, tough acting, tenacting, you spray it on your feet. So that would be dust, like a powdered dust mixed in with the gas. That would be a solid aerosol, as opposed to like a liquid aerosol. Foam, like whipped cream. It's mainly a liquid, but they fluff it up, they pump it full of gas. So it's not a solid liquid or gas, it's kind of in between these two. It would be a foam. Mayonnaise, you've got liquids kind of mixed in with liquids. They kind of mix, but they kind of don't. That's an emulsion. Latex paint, they take solid. They mix it in with the liquid. So it's like a liquid, but when the liquid leaves, it leaves the paint particles behind on the wall. So that's called a sol. We're getting pretty close to Thanksgiving. What do you do with like turkey fat on the stove? Oh, liquid turkey fat. I love dumping that on mashed potatoes. Oh, it's gravy. How do you make gravy? Which is liquid turkey fat. It's all like the turkey fat that dripped into the bottom of the pan. You just chuck that on mashed potatoes? No, you stick it on the stove, you heat it up, and then what do you stir into it? Anybody ever make gravy? Okay, cornstarch. Maybe watch your parents or grandparents this year, or if you make gravy, anybody making the gravy, watch, see if you can help. You add cornstarch, which is a solid, or you add flour. So a liquid with solid mixed in, you're making gravy, which is really a sol. Not a solution, but it's related, so it's a sol. And then foams. Down here we got some foam. So like packing peanuts. It's mainly a solid that's kind of airy. That would be a solid foam. Next week, once I have enough samples, I just got the final paperwork approval from the district. I can't hand out or pass out any food items in the class because I guess it could be, you could be allergic and could die, or if you would eat a piece, that would put you over your calories for the day. So we don't want to do that. But I got approval that I can like pass around some yogurt melts that we freeze dried. I can pass around some astronaut ice cream sandwiches. I'm not sure where they got to. I can pass those around in a baggie. They're basically solid, that all the moisture has been removed, leaving little air pockets. So you'll be able to see what that solid foam looks like. And I got special permission that I can't let you eat it in class, but if you'd stop down at the end of the day at like 3:06, when I'll let you know next week, you could take a sample, and as you leave the building, then you could eat it because that would not be toxic and that would not put you over your calories for the day. So we did get approval to do that. So I'll let you know once they've all been made. But you actually get to kind of eat one of these solid foams. It's called an aerogel. Any questions on colloids? So basically, life is always more complex than what we make. All right, let's talk about solutions, because this will be the solution to basically all of your homework answers. A solution is made up of two parts. The top, the solid that you're mixing into the solution, is called the solute. You add the solute and dissolve it. And the solvent is what you're adding it to. So usually there's a little bit of solute and a lot of solvent. The way I remember that, the difference, you add the solute to dissolve. And in paint, you often kind of smell those solvent fumes as they're evaporating. So you go to the window and vent those fumes out. So the solvent needs to evaporate and leave. The solute would be like the solid that's left behind. So this is just some vocabulary. So I thought this was kind of cute. That was your solution. Now, just in case you're looking at this and kind of seeing two things mixing together, really so it's almost like the solid's in love with the solvent. Before this happened, what should the solute have done? It should have asked for consent. You just don't hop into the liquid and dissolve yourself. It should have said, hey, I think we would make a good solution. You care if I hop in here? You care if we mix it up and make a homogeneous solution? So it really should have asked for consent first when you mix things. Again, if you're confused, just ask your parents about it. All right, how do you fix all of your problems? Wait for it. Wait for it. You dissolve that. Yeah, you dissolve them. Okay. I made that one up. I came up with that. All right, solubility. This is your homework. What do we mean by solubility? It's the maximum amount of solute that you can add to a solvent. You can't just keep adding more and more and more and more solute. At some point, you're going to reach your maximum, and you won't be able to dissolve anymore. So it'll just settle out on the bottom. So there's two types of solutions, saturated and unsaturated. Saturated means you've dissolved the maximum amount. At that temperature, under those conditions, you can't dissolve any more chemical. So imagine putting sugar in Kool-Aid. You mix it up. Great, it dissolves. You add some more, mix it up, it dissolves. Add more, mix it up, it dissolves. At some point, you're going to add so much sugar, it settles on the bottom. At that point, that solution is saturated. Every point up to that, it would be unsaturated. If you can add more and it's not saturated, it would be unsaturated. You might think those are the only two circumstances, but if you take a look at the EQ, how many types of solutions are there? 3. So saturated, unsaturated. Can anybody think of another prefix that would give us a third one? There's people, there's heroes, and then there's what? That's Spider-Man, Thor. They're not just heroes, they're superheroes, right? So you could be saturated, but you could trick the solution into dissolving extra chemicals, and then it would be super saturated. I won't have time for the demo today, but I'll start out class with that on Monday. So I'll do the demo on Monday. Examples would be fudge, rock candy, hand warmers. I'll show you my super saturated solution of sodium acetate. So oftentimes if you heat up the solvent, you can dissolve extra chemical, and then if you slowly cool it down, it'll stay dissolved, and at that point it's extra saturated or super saturated. All right, this right here is your homework. It's a solubility curve. It's a graph, and you need to know how to read that graph. At every temperature, it tells you the maximum amount of chemical you can dissolve. So let's read it. At 50 degrees Celsius, where do I see temperatures up here? Y-axis? Oh, x-axis, down here, 50 degrees Celsius. Would you agree there's a lot of chemicals up here? We probably don't have to look at every chemical for every problem. Which chemical do we want? Table salt. So let's outline that. Here is our table salt. We're going to go up at 50 degrees Celsius to find our chemical. And how do we read this graph? we go to the y-axis. What number would you write down? Right about there. Somewhere between 30 and 40. Best guess? 30. I think it's a little bit higher than halfway. 37, 38. I'm not going to argue sig figs, okay? It's allowed to be uncertain. Let's go with 37. What does that 37 mean? 37 grams of the solute. Well, what's our chemical? Salt. For every, solubility is a fraction, for every 100 grams of water. So imagine this. You have a cup of 100 grams of water. It's pretty warm. Body temperature is 37. This is warmer than that, 50. And you'd be able to dissolve 37 grams. Does that answer the question? At 50 degrees, how much table salt can be dissolved in 200 grams of water? Ooh. Right. So the solubility is the ratio, the fraction. This problem wants to know at 200 grams. So we're going to have to double the answer, which would be what, 74? 74. So the answer is 74 grams of salt. If you go any over that, it's just going to keep settling on the bottom. So you'll have salt water that is saturated and then just clumps of salt on the bottom. Any questions on that graph? Your homework is going to be page 27. There's a big graph. You're going to use that graph to answer, is it 9 questions on page 28? Are there 9 questions? I think there's 9. Yep, that's it. That's the lesson. Any questions?